When you hear the word camouflage, your mind probably jumps to an animal hiding in a forest, right? Or maybe a soldier in the jungle. But it's so much more than that. The principles of camouflage are a driving force in art, they're a political statement in war, and the secret to one of its most famous examples, well, that's written in a single rogue piece of DNA. Okay, let's get into this. Just take a look at this. Can you even see it? This is a mossy leaf-tailed gecko. And it's not just the color and texture that make it vanish. If you look really close, it even has this little fringe of skin along its body to flatten its own shadow. It's literally erasing itself from three-dimensional space. I mean, this isn't just hiding. This is a total mastery of illusion.
And that leads to the big question, one that has fascinated scientists and artists for centuries. How does an animal with no conscious thought, no art class, achieve this perfect level of invisibility? Well, the answer is a story that unfolds over millions and millions of years.
So here's our plan. We'll start with the science of hiding, then get into the evolutionary arms race that powers it. We'll explore nature's incredible bag of tricks, jump over to the human battlefield, meet the artist who basically became the father of camouflage theory, and finally, we're going to decode the secret genetics of one very famous moth. All right, let's start with the basics. What are we really seeing when an animal just seems to disappear right in front of us? Okay, so the fancy scientific term for this is crypsis. And it's not just about what you see or, what you don't see. Crypsis can be visual, yeah, like our gecko, but it can also be about smell, hiding your scent from a predator that hunts with its nose. Some animals, like the puff adder, have even evolved a kind of chemical crypsis, which makes them nearly undetectable. It's a full-on, multisensory disappearing act. So how does an entire species get so ridiculously good at this? I mean, they're not going to camouflage school. The answer lies in one of the most powerful forces on our planet. And this is the most important thing to get. An animal doesn't decide to develop camouflage. There's no intention there, no artistic vision. Instead, it's the passive, almost inevitable result of this brutal, high-stakes filter we call natural selection. I absolutely love this quote I found on Reddit of all places because it just nails the whole concept perfectly. It completely flips the question around. It's not about how they actively develop it. The reality is much simpler. The ones who aren't well camouflaged, well, they just don't get to pass on their genes. It's this simple, relentless cycle. It all starts with random variation, right? No two animals are exactly the same. Then comes the pressure. A predator is looking for lunch. That leads to the survival of the best adapted. The one that's just a little bit harder to spot gets away. And then, the most important step of all, reproduction. The survivor passes on those harder-to-spot genes. Now, just repeat that process for a million years and you get that gecko. And what this creates is this constant back and forth. As the prey gets better at hiding, the predators are under pressure to evolve better eyesight to find them. And as the predators get better at seeing, the prey are under even more pressure to get even better at hiding. It's this endless, self-fueling arms race that drives some of the most incredible adaptations you'll ever see. But, just matching your background color? That's just Camouflage 101. This evolutionary arms race has produced an absolutely mind-blowing variety of strategies. The sheer creativity here is amazing. You've got disruptive coloration. These high contrast patterns that don't blend in but actually break up the animal's silhouette so it's hard to even recognize as an animal. Think of a leopard's spots. Then there's countershading. Dark on top, light on the bottom. It cancels out the sun's natural shadows, making something like a shark or a penguin look totally flat from above or below. Mimesis is all about looking like something boring, like a stick insect or an orchid mantis that looks exactly like a flower to ambush its prey. Then you have self-decoration. Decorator crabs literally cover themselves in sponges and anemones from their environment. And in the open ocean, where there's nowhere to hide, some creatures have evolved total transparency, while others have silvered sides that act like a mirror, just reflecting their surroundings. It's incredible. For centuries, humans have tried to copy these amazing strategies from nature, and nowhere more than in the theater of war. But the story of military camouflage shows us it's about a lot more than just hiding. For most of history, military uniforms were bright, loud, and designed to look impressive. But with the invention of more accurate rifles, that basically became a death sentence. Back in 1800, a British officer figured out that gray targets were hit half as often as red ones. By the mid-1800s, the British in India adopted khaki, which is a Hindustani word for soil. The really big shift was World War I.
The French army went into battle wearing bright red trousers and took absolutely devastating casualties, forcing a quick switch to a much less obvious horizon blue. By World War II, complex printed patterns were becoming the norm, and today, they're standard issue everywhere.
So this all seems purely functional, right? You get better at hiding so you don't get shot. But is that the whole story? Or can a pattern that's meant to conceal you also be used to reveal something really important about who you are? To answer that, let's look at this key moment in modern history, the collapse of the Soviet Union's military alliance, the Warsaw Pact. As these former Soviet bloc countries started to realign themselves with the West, researchers noticed this strange, subtle shift, not in their policies, but in their patterns. And this chart just lays it all out, clear as day. Researchers analyzed the uniforms from countries like Poland and Hungary. Before 1991, their patterns were their own thing. After 1991, their new patterns became statistically way more similar to the ones worn by NATO countries. They started to look like their new friends. So the key takeaway is, this wasn't just about getting a more effective pattern for hiding in the woods. It was a visual signal. By adopting camouflage that looked like NATO's, these nations were sending a powerful political message to the entire world about where their loyalties were now. The very tool of concealment became a tool for signaling identity. This idea that camouflage is really about manipulating perception brings us to this remarkable and honestly pretty controversial figure, a man who argued that to truly understand concealment, you couldn't be a biologist. You had to be an artist. This is Abbott Henderson Thayer. He was a successful American artist around the turn of the 20th century who became completely obsessed with coloration in nature. And he basically believed that biologists were missing the whole point because they weren't trained in what he called optical illusion, which is the very essence of what a painter does. He saw nature as the ultimate artist. And his artist's eye led him to 3 foundational theories that we still use today. First, countershading, which we talked about, the idea that shading can make a 3D object look flat. Second, disruptive coloration, where bold patterns shatter an animal's outline. And third, dazzle. This was his most radical idea, especially for the military. He proposed painting ships, not to hide them, but with these wild, confusing stripes to make it impossible for an enemy submarine to judge their speed and direction. It was all about confusion, not concealment. Thayer was a genius, no doubt. But he was also, well, he was a bit of a zealot. He became so convinced of his theories that he started arguing that all animal coloration was for concealment. He famously insisted that pink flamingos were camouflaged against the pink sky of a sunset, completely ignoring that they're, bright pink and incredibly visible the entire rest of the day. This overreach made a lot of scientists dismiss him, but it doesn't change the fact that his core insights were decades ahead of their time. Okay, so we've seen the what and the why of camouflage. We've seen how it works in nature and in human culture. For this last section, we're going to the deepest level possible, the how. The precise microscopic event that can change the evolutionary course of an entire species. You've probably heard of the peppered moth. It's the classic textbook example of evolution in action. Before the Industrial Revolution in Britain, most of them were light-colored to blend in with trees. But as factories pumped soot into the air, the trees turned black, and suddenly the rare dark-colored moths had the advantage, and they quickly took over. But here's the part that story always leaves out, and it's the most incredible part. Natural selection can only work on variation that's already there. So where did that first dark moth, the one that started it all, even come from? What was the genetic spark that created the raw material for evolution to play with? Well, the answer, and scientists only figured this out recently, is this. Now, I know this looks complicated, but what you're looking at is a single, massive, and totally random genetic event. The mutation that turned the peppered moth dark wasn't some tiny typo in the DNA. No, it was caused by a huge chunk of mobile DNA, a jumping gene, that literally cut and pasted itself into a critical spot in the moth's genome. Let's just walk through it. First, you have this intruder, this transposable element, just hanging out in the moth's DNA. It's like a rogue piece of code. Second, it targets a very specific gene, one that just happens to control wing patterns. Third, in this crazy cut-and-paste moment, it slices open the chromosome and shoves its own massive code right into the middle of that gene. And fourth, that one insertion completely rewrites the instructions, creating a brand new allele, the genetic command for black wings. And this is the absolutely breathtaking conclusion. One of the most iconic stories of natural selection we have wasn't the result of some slow, gradual change. It was sparked by a single, lucky, random leap of a rogue piece of DNA. This one event created the variation that, when the world changed, allowed the peppered moth to survive.
So we've gone from the incredible artistry on a gecko's skin to the politics hidden in a soldier's uniform, all the way down to a single jumping gene that rewrote a species' future. It really makes you wonder, doesn't it? In a world that's so full of surfaces and patterns and signals, what other hidden stories are right there in front of us, just waiting to be seen?